Welcome to qnawire.
In this problem, we have a sports car traveling at 100 miles an hour, and it's going over a hill that is, let's see here. It's going over this hill, and so we have something like it's coming up this hill, and the hill's rounded off at the top. And so then we have a radius of curvature for this hill here. And that radius is something we are needing to determine. Now, let's see here. The car, the initial car, the sports car, weighs 2,400 pounds. And let's see here. All right, and it's going at, let's see here, I didn't write that down. V was 100 miles per hour, and that equals 147 feet per second. All right. So let's see here. We have, we're told that as it starts going over this hill, it just loses contact with the road. So it kind of just gets airborne. And when it reaches this crest of the hill, okay? And again, I'm not sure. Well, it's a little bit drawn off to scale because the hill is kind of like the length of the vehicle. So I'm not sure what they mean by it reaches the crest of the hill. I guess by the time that maybe one tire is here, one tire is here, so the whole vehicle is going over. Anyway, these are both 0. And so if we draw a free body diagram of the vehicle, and again at the crest it's just horizontal. You have the weight, the normal force. These are 0, so the weight has to equal the mass of the vehicle times the radial acceleration, which is v squared over rho, which means that rho has to equal v squared over g. And plugging in all our values here and then g, we get 668 feet. So that is the radius of curvature of this this part of the hill, the crest of the hill. Now, we're told that for that same hill, determine the force exerted on a 140-pound driver by the seat of his 1,300-pound car as the car is traveling at a speed of 50 miles an hour passes through A. So basically, exact same situation, but now we're going to look at the driver of this vehicle. And there's a normal force on the driver, the weight of the driver, and then the radial acceleration. And since we know that it's a constant speed, the tangential acceleration is 0. 50 miles an hour is 73.3 feet per second. So a free body diagram says that W prime minus N equals the weight or the mass of the driver times V squared over rho. We can solve for N here, plug in omega prime, because we know that. We know rho from here. V squared is here, and we know G, and that turns out to be the weight, the apparent weight, or the normal force on the driver from the seat is simply 120 pounds. So basically the driver looks like the effective weight is less. So if you put a scale in here, you would only measure 120 pounds instead of 160 pounds when you're on going in a line.